Lisp, the ancient alchemist of programming. Born in 1958, Lisp stands apart because it is the language of eternal flexibility, looking less like English and more like a dense, complex series of nested parentheses, a primordial soup of code. This uniform structure, where everything is an S expression, symbolic expression, means that code and data are treated identically. This simple, radical concept unlocks its most powerful secret: metaprogramming through macros. Lisp doesn't just let you write a program. It lets you write a program that can write or modify other programs, effectively allowing you to instantly build a new, perfect language tailored precisely to your problem, all inside Lisp itself. This made it the ultimate tool for artificial intelligence pioneers and complex symbolic reasoning systems. While most languages constrain you to their rules, Lisp hands you the toolbox to rewrite the rules, proving that sometimes the oldest ideas offer the deepest, most adaptable power. Consider Haskell. Haskell is a purely functional programming language developed in the late 1980s with the goal of creating a common standard for functional languages being studied at the time. Haskell is the Stoic philosopher operating in a state of absolute mathematical purity. Born from academic rigor, Haskell champions purely functional programming. This means your functions are rigidly side-effect free. They don't interact with the outside world, they don't change global variables, and for any given input, they will always produce the exact same, predictable output. This profound philosophical discipline eliminates the entire class of intermittent, hard-to-find bugs caused by unpredictable changes, the kind of chaos C++ developers dread. Haskell is also famously lazy, meaning it won't perform a calculation until the result is absolutely needed. This is not laziness but extreme, high-efficiency computation. It's the digital equivalent of waiting for the perfect moment before committing an action, ensuring no single CPU cycle is wasted. Learning Haskell forces you to think in a mathematically precise way, creating systems that, once they pass the test of the compiler, are nearly guaranteed to be correct, teaching the profound life lesson that purity of purpose leads to unshakable certainty. Python is, without a doubt, the golden retriever of programming languages. It's friendly, relentlessly approachable, and somehow capable of everything from fetching your slippers, automating a simple task, to landing rovers on Mars, powering complex scientific simulations. It's the language of unconditional digital love. The brilliance of Python traces back to its creator Guido van Rossum in 1991. He gave Python one simple, revolutionary job: make code readable. Before Python, coding often felt like writing cryptic, esoteric riddles that only a few initiates could decipher. The code was choked with curly braces, semicolons, and strange symbols, creating a high barrier to entry. Python swept all of that away. It forced a structure on the code using indentation instead of arbitrary symbols, creating a syntax where you write logic almost like English, and it just works. This commitment to clarity is more than a stylistic choice. It is a profound philosophical statement crystallized in a document known as the Zen of Python, which starts with the mantra, "Beautiful is better than ugly. Explicit is better than implicit." Because of that immediate clarity, Python rapidly became the go-to language for beginners, the core tool for educators, and the chosen workhorse for professionals who needed to translate an idea into a working product fast. Today it's not just popular. It's an institutional pillar, automating small tasks and powering billion-dollar applications across every single industry you can name. What truly elevates Python from a beginner's tool to an industrial powerhouse is the staggering scale of its ecosystem. Think of it as a vast, interconnected digital city. Python didn't just give us a car. It gave us a car and a pre-built highway system connected to specialized factories. Need to sift through mountains of financial data? You use NumPy and Pandas. Planning to build a recommendation engine that knows your mood better than you do? You'll deploy TensorFlow and PyTorch for machine learning. Developing a new social media or streaming site? You're leaning on Flask or Django for web development. Companies like Netflix, for instance, use Python far beyond just their recommendations. They use it for their sophisticated content delivery network, CDN, which determines the perfect video quality for your device at any moment, and for the security tools that protect your account. NASA relies on it daily, not just for simulations, but also in the very equipment control systems that communicate with probes billions of miles away. This unmatched versatility means you can use the same language to analyze satellite data, build a secure web service, and write an automation script that reorganizes your desktop, all before your second cup of coffee. Of course, every hero has a flaw, and Python harbors a dirty secret. It's slow. Not slow like a sloth, but slow compared to the blistering, microscopic speed of languages like C++. Developers specializing in high-performance computing often look at Python code the way a Formula One driver looks at a golf cart. It gets you there, but with agonizing deliberation. The reason for this slowness is often tied to the global interpreter lock, seal, which, in simple terms, prevents Python from running multiple threads, mini-tasks, fully in parallel. This trade-off, however, ensures the language remains incredibly simple and thread-safe to write, avoiding the nightmare of concurrent programming that haunts C++ and C developers. The secret is, truly, nobody cares about the speed difference for 95% of tasks. Python's speed is measured in developer time, not processor time. A task that might take 100 lines and a full day in Java or C++ can often be done in 10 lines and an hour of Python. It's the difference between trying to build a complex structure by carving each individual brick by hand, C++, versus simply snapping pre-made Lego pieces together, Python. The result is that Python scales perfectly with the average user. You can start with basic scripting, and without ever switching languages, you can move into full-stack development or advanced artificial intelligence. It's accessible to the newcomer, but deep enough to keep the expert challenged. If Python is the golden retriever, then C++ is the programming equivalent of an utterly unrestrained, perfectly engineered beast. It is the language that can do absolutely anything, but in doing so, will absolutely give you the power to destroy everything. It's the digital equivalent of handing a new hire a chainsaw, a flamethrower, and a nuclear reactor saying, "Good luck," and walking away. With C++, you have the godlike ability to micromanage how every single byte of memory is used, allowing you to optimize performance down to the very nanosecond. But with that power comes a terrible fragility. You also possess the ability to accidentally corrupt your entire program because you misplaced a single semicolon. Or, far worse, forgot to clean up a memory pointer deep within your code. The inherent structure of the language is so vast and complex that two different master developers can write the exact same program in C++. Both can be technically correct, and yet both can be impossible for the other to read without months of painstaking study. C++ was born from necessity in the mid-1980s. Software was no longer a few pages of simple code. It was growing into entire novels, massive systems that plain C, with its unstructured, procedural approach, couldn't handle. Writing these behemoths in C felt like trying to perform brain surgery with a flathead screwdriver. It was tedious, error-prone, and unsustainable. Bjarne Stroustrup created C++, originally C with classes, to take everything blisteringly fast about C, and turn it from pure chaos into organized chaos. The revolution was the introduction of object-oriented programming, OOP. This concept, now ubiquitous, allowed developers to bundle data and functions together into self-contained objects. Suddenly, you weren't managing a single, sprawling mess of logic. You were designing a system of small, organized, self-sufficient components that could interact cleanly. It allowed software to be designed like a complex machine with moving parts, not a single giant sheet of instructions. By the 1990s, C++ became the undisputed standard. It was the backbone of virtually every major desktop application. Microsoft Windows, Adobe Photoshop, Autodesk Maya, and Mac OS X all relied on it. It didn't just power operating systems and desktop software. It fueled the first generation of immersive 3D games, a space where speed is not negotiable. And it hasn't retreated since. Today, the physics engines that run games like Fortnite and Final Fantasy VII Remake are built into the Unreal Engine, which is C++. Core parts of Google Chrome's rendering engine, Amazon's massive back-end systems, and Facebook's core infrastructure are all quietly powered by C++. The true domain of C++ is where performance is not just a nice-to-have, but a matter of competitive survival. This is why it's the king in quantitative finance and high-frequency trading. When a millisecond of latency can translate into millions of dollars in lost revenue, fast enough means written in C++. It has the only language that allows you to get so close to the hardware that you can fine-tune every CPU cycle. The price of this control is the immense complexity. C++ hands you a massive toolbox, classes, templates, operator overloading, multiple inheritance. It's not that C++ is inherently difficult. It's that it gives you so many sophisticated options that you end up debating yourself at 3 o'clock a.m. over which one is technically the best, most elegant, and most optimized solution. The learning curve isn't a curve. It's a sheer cliff face. Alright, let's talk about Java, the language that refuses to die because it never stops working. Java is the programming language equivalent of the impeccably reliable middle manager who wears a tie to Zoom calls, has been successfully running Fortune 500 companies for 30 years, and absolutely, positively is not going anywhere. It's not flashy, but it is the invisible glue that holds the modern corporate world together. Born from Sun Microsystems in 1995, Java's promise was the impossible dream of the software world. Write once, run anywhere. This was a radical idea in an era dominated by languages like C and C++, where code had to be meticulously recompiled and often rewritten for every single operating system, Windows, Mac, various Unix systems. Java, for the most part, delivered on this impossible promise. The structure of Java is its most defining trait, and often the source of its mockery. In C, you can print "Hello World" in one line. In Python, maybe two. In Java, you are immediately required to declare a public class, define a static void main method, import system out, and basically write a legal document just to achieve that simple greeting. This verbosity is not arbitrary. It has a profound purpose. When you're managing a colossal code base with 50 developers distributed across 10 different time zones, Java's rigorous, heavy-handed structure forces clarity and consistency. Everyone is forced to write code the same, structured way. There are no surprises, no room for creative, high-risk solutions that can shatter the entire application. That's why the most stability-obsessed organizations, banks, airlines, insurance companies, and government agencies don't just love Java. They rely on it for their very existence. They choose Java because code written in 2006 still runs today and will likely outlive us all, running on ancient hardware with the same predictable results. The key to Java's immortality is the Java Virtual Machine (JVM). Instead of compiling directly into machine code that speaks only to a specific operating system, Java compiles into bytecode. The JVM acts as a universal translator, a digital air traffic controller that lets the same bytecode program work seamlessly on Windows, Mac OS, Linux, or even your smart fridge. While running the JVM might make your laptop sound like it's just taking off as it fires up its engines, performing just-in-time compilation, the benefit is that once it runs, it will keep running, reliably, securely, and predictably. Another foundational feature is garbage collection, GC. In C or C++, memory management is the developer's burden. A single forgotten free command leads to a memory leak and catastrophic failure. Java's GC is the benevolent, though sometimes disruptive custodian who automatically takes out the trash, managing the memory behind the scenes. This allows developers to focus on the business logic, not the delicate details of the hardware. Boring, reliable, and absolutely not going anywhere. That's the legacy of Java. If programming languages were people, JavaScript would be the charming, unpredictable friend who somehow manages to get everything done, even though no one including them understands exactly how they did it. It is the chaos agent that became the cornerstone of the internet. JavaScript's history is famously chaotic. It was created in a frantic, astonishing 10 days in 1995 by Brendan Eich at Netscape, simply to make websites interactive. The initial brief was tiny: animate a button, validate a form. Today, it powers an estimated 98% of the web. It handles the front-end interactivity, everything you click, swipe, and scroll, and, thanks to the creation of Node.js, it even runs the servers on the back end. Even the very video player you are using right now is most likely using JavaScript somewhere deep behind the scenes. Here is the paradox. JavaScript makes no rational sense. Developers often call it a forgiving language. What they really mean is that it silently lets you destroy everything without throwing a helpful error. It is infamous for its coercion, where the language tries to guess what you mean, often with disastrous results. Running 1 + 1 doesn't give you an error. It gives you the string 11. Running 1 + 1 gives you 2. The language is a minefield of unpredictable assumptions. But despite its quirks, or perhaps because of its initial simplicity and low barrier to entry, JavaScript became unstoppable. Its true magic is that it runs natively in every browser, meaning every single computer with internet access is a JavaScript environment. This universal platform made it the default for every major website, online tool, and front-end framework like React, Vue, Angular, and Next.js. Performance-wise, JavaScript began as a toy, notoriously slow and single-threaded. However, the advent of Google's V8 engine, the blazing-fast open-source JavaScript engine that powers Chrome and Node.js turned the language from a simple toy into a legitimate powerhouse. Suddenly, you could build sophisticated, real-time applications, 3D games, and high-throughput backend APIs entirely in JavaScript. The developer's experience, however, remains a wild, chaotic ride. 1 minute, everything is working perfectly, and the next, you are staring at the dreaded console error. Undefined is not a function and questioning every life choice that led you to that moment. Still, for anything related to the web, JavaScript is king. You can love it or hate it, but you absolutely cannot escape it. The comment section, the like button you're about to click, it's all JavaScript. If JavaScript is the unpredictable artist, then TypeScript is what happens when that artist finally realizes they need an organized studio, an accountant, and a therapist. By the early 2010s, web applications were colossal. What started as small scripts to animate a few buttons had morphed into full-scale, 1,000-file applications, and JavaScript's forgiving nature became a massive liability. The silent errors of JavaScript were letting developers ship mission-critical bugs to production like it was their primary job. The bigger the app got, the more catastrophic the hidden bugs became. That's when Microsoft, the corporate giant, stepped in with TypeScript. The mission was clear. Not to replace JavaScript, but to fix it. The core idea was simple but revolutionary: add static typing. In plain terms, TypeScript acts as a dedicated quality control desk for your code. While JavaScript lets you pass anything to any function, a number, a string, a picture of a cat, TypeScript checks every single variable, function, and parameter before the code ever runs. If you accidentally pass a string where your code is expecting a number, TypeScript screams at you immediately, right there in your editor. This prevents the disastrous scenario of your website crashing during a live demo because of a fundamental type mismatch. This single feature changed everything for large-scale JavaScript development. Suddenly, applications with hundreds of thousands of lines of code became manageable. The language forced developers to document their code implicitly by defining the types, allowed them to spot mistakes instantly, and provided the confidence needed for advanced tooling like auto-completion in the editor. TypeScript compiles down to regular, clean JavaScript, a process called transpilation. This is the genius of it. There is no performance penalty because what ultimately ships to the user is still plain, universal JavaScript. The impact was immediate and massive. Frameworks like Angular, and later Next.js and React, all added first-class TypeScript support. Tech titans like Google, Slack, Airbnb, Asana, and Microsoft now use it across their front-end and back-end systems. It has become the gold standard, the undeniable default for any serious, large-scale web project. By 2025, surveys indicated that a huge majority of professional web developers were using TypeScript in production, a testament to its value in bringing stability to the chaotic web frontier. Created by Mozilla in 2010, Rust had one almost messianic mission: deliver C++ performance without the C++ disasters. It is a systems programming language designed to work intimately close to the hardware, but with one critical, non-negotiable difference. Safety comes first. The secret to Rust is its uncompromising security system called the borrow checker. This is not just a feature, it's a philosophical stance. The borrow checker is a merciless, brilliant gatekeeper that enforces memory safety at compile time. It tracks how every single piece of data is accessed, ensuring you never use invalid references and crucially preventing data races. A common vulnerability in C++, where two concurrent tasks try to modify the same memory at the same time, leading to crashes and security holes. The Rust developer experience is legendary for its difficulty. The process is often described as, you write code. The compiler says no. You fix it. The compiler says no again with 47 pages of esoteric instructions. You fix it again, spending hours placating the compiler. Here is the magic. Once it finally compiles, with absolute certainty that your code is rock solid, you have proved its safety to the machine. Rust has, quite remarkably, topped the Stack Overflow Most Loved Language survey for 8 straight years. Developers love it, not because it's easy, but because once they master its strict discipline, they realize the security and speed are unparalleled. Rust delivers the raw, blazing speed of C++ coupled with the security and guardrails of a modern managed language. The world has taken notice. Mozilla used it to rebuild parts of the Firefox browser, making it faster and more stable. Giants like Amazon, Microsoft, and Dropbox have adopted Rust for their most performance-critical components. The most monumental endorsement came in 2022 when the Linux kernel, which had been written almost entirely in C for over 30 years, officially began integrating Rust support. This was a massive historic milestone, signaling that safety is now a top-tier priority, even at the deepest levels of computing. Rust truly shines in concurrency. Its rules allow you to write code that runs multiple tasks at once without the possibility of them interfering with one another. While C++ might allow 2 threads to corrupt the same memory, Rust simply refuses to compile code that is inherently unsafe. This makes it ideal for modern workloads, cloud computing infrastructure, high-performance game engines, and, critically, blockchain systems, where a single crash could result in the loss of millions of dollars of real money. The learning curve is steep, and developers often say mastering. Rust is like learning to think about programming differently. It requires less improvisation and more rigorous, upfront discipline. But once mastered, it is profoundly empowering. C isn't just a programming language. It is the godfather of programming languages. It's the one every other language from C++ to Go, Rust, and even Python either learned from, stole from, or is still paying deep, fundamental tribute to. C is the silent reason your phone works, your car starts, and the Mars rover didn't smash into a canyon wall. C was born in the early 1970s at Bell Labs, created by Dennis Ritchie to rewrite the Unix operating system. Up to that point, Unix was written in assembly language, which was basically programming using raw machine instructions, painful, tedious, and one misplaced instruction away from frying your system. C changed the game forever. It offered the raw speed of assembly, but provided the revolutionary readability of English-like syntax. This was a tectonic shift. Suddenly, developers could write portable code. This meant a program written for one machine could be easily moved and compiled on a completely different type of machine without being rewritten from scratch. That one idea portability made C unstoppable. By the 1980s, C was everywhere, forming the base of Unix, powering Microsoft Windows, and influencing Mac OS X for decades. Today, if you use Linux, the Linux kernel is almost entirely C. The interpreters for Python, Ruby, and PHP are all written in C. Even modern browsers like Chrome and Firefox rely on C for their high-speed rendering engines. Why does it endure? Because C talks almost directly to the hardware. There are no virtual machines, no garbage collectors, and no safety nets. When you write C, you are practically whispering instructions into your CPU's ear. You, the developer, decide precisely how memory is used, when it's cleaned up, and how every single byte moves through the system. That control is exhilarating, but it is also the most dangerous thing about the language. Forget to free up memory and you've created a slow, agonizing leak that will eventually choke your entire system. Right past the boundary of an array, and you've opened a door for a hacker. Entire global cybersecurity breaches have been traced back to tiny negligent C mistakes. The infamous Heartbleed bug in 2014, which exposed private keys and sensitive data across millions of websites, was caused by a simple memory handling error in the OpenSSL library, all because of one unchecked buffer size. That is the unyielding trade-off C demands. Absolute power and precision come with zero forgiveness. Yet this is why it endures. C is used anywhere performance is the absolute critical factor. Operating systems, databases, embedded systems, your smartwatch, router, car's engine control unit, and network drivers. It is not beginner-friendly, and it will not hold your hand. But learn C, and you will see, for the first time, how a computer really thinks. Finally, we arrive at Go or Golang, the language born out of pure engineering pragmatism. Go is what happens when Google's most brilliant engineers get tired of waiting for their massive complex codebases to compile. Their goal was simple: build a language that's fast, clean, and doesn't make you want to throw your laptop out a window. It is not trying to be the most clever. It is only trying to be the most efficient. Go is best thought of as the Tesla of programming languages: clean, minimal, lightning fast, and utterly predictable. The language's core purpose is to handle massive concurrent workloads, millions of requests per second, without falling apart. The evidence of its success is everywhere in the modern cloud. Docker, the tool that single-handedly revolutionized how we deploy and package software, is written in Go. Kubernetes, the system that orchestrates those millions of containers across vast data centers, is also written in Go. Companies like Google, Uber, Dropbox, and Cloudflare use it for their core services that need to handle millions of requests per second without a moment of lag. Syntax-wise, Go is deliberately clean and strict. Unlike C++ or Python, there are very few ways to accomplish the same task, and the compiler enforces this singular consistency. This lack of stylistic flexibility is a feature, not a bug. It means teams can collaborate seamlessly without debating code style for 3 meetings straight. The consistency ensures that every line of code looks familiar, regardless of who wrote it. Critically, Go compiles at a blazing speed, deploys with astonishing ease, and the resulting programs are tiny, self-contained binaries. This means no dependency nightmares, no complex installers, and no works on my machine drama. You just run it, and you go. The secret to its performance lies in its unique approach to concurrency called goroutines. While other languages rely on heavy, expensive operating system threads, like a handful of jumbo jets, goroutines are extremely lightweight, inexpensive functions, like thousands of paper airplanes that allow a Go program to handle concurrent operations with incredible efficiency. Developers love it because it just gets out of the way. It solves the hard problems of network services and leaves them to focus on their actual application. We have journeyed through 10 distinct philosophies, 8 ways of thinking that, together, built the digital world. Each language represents a successful, enduring answer to a fundamental problem. LISP demonstrated the power of flexibility and metaprogramming. Haskell enforced the power of purity and mathematical certainty. Python answered the call for clarity and ease of use. C++ was the answer to the need for ultimate control and speed. Java gave the world reliability and a scalable corporate structure. JavaScript seized the moment of necessity and ubiquity on the web. TypeScript proved the power of self-correction and type safety. Rust created the blueprint for unbreakable discipline and modern security. C established the bedrock of fundamentals and talking to the machine. Go defined the future of efficiency and concurrency at scale. These languages are more than just syntax. They are living metaphors for how we approach our own lives and work. The lesson for you: you are constantly coding your own reality. Are you approaching your new projects with the low-friction accessibility of Python, ensuring clarity and speed to market? Do you have areas in your life, like your finances or health, that require the rigid, zero-tolerance discipline and safety checks of Rust? Are the foundations of your career built on the absolute fundamentals learned from the hard lessons of C? Or are you wasting time with the verbose, overly complex bureaucracy that is not Java, but simply unnecessary complexity? The most powerful developers are multilingual. They know when to use the C++ chainsaw, the Python Lego kit, or the Go Tesla. The most successful people in life understand the same principle. They deploy the right mindset for the task at hand. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.